In this video, we're going to talk about graphical behaviors of functions. So there's some key things that functions do that we can study that are useful to us, especially for those moving into calculus. So let's start by talking about this concept of increasing and decreasing. So a function is increasing on an interval if the function values increase as the inputs increase. So here, I'm going to draw a small picture of what that means. So let's say we'll look at like a half parabola here, something like this. Okay, so here's the idea. There's a point on the parabola, and that point will be A, and we'll call this one f of A. So we'll assume that the red graph is f. That's f represents that function. Okay. Increasing means that if I put in a bigger input value, so something to the right of A, like call it B, then its output, its Y value is going to be bigger than the Y value for A. So f of B is bigger than f of A. Well, that's what this statement says here, that f of B is bigger than f of A as long as B happens to be bigger than A. And what that does then, in terms of the average rate of change in the function, it's going to end up being a positive average rate of change. Now, decreasing. So a function is decreasing on an interval if the function values decrease as the inputs increase. So the inputs are still increasing in value, but the difference is the Y values are not. So let's look at an example of that. So let's look at this. We'll do the opposite, kind of an upside down parabola. So again, here's A, and that'll be f of A right there. B, still bigger than A, but f of B is not bigger. That is when it's decreasing in value. So f of B is not bigger, even though we put in a bigger input. In that case, the average rate of change comes out negative. Okay, so let's put this information into an example. Let's say we have this function here. We want to know when this function is increasing. So this thing looks like it's increasing from 1 to 3, from there to there, and then again from 4, and then technically it goes on forever. So in interval notation, this thing would be increasing from 1 to 3. I'll go ahead and erase my big highlighting there. 1 to 3, and then again, so I'll use the union symbol, from 4 to infinity, because that's where the graph appears to be climbing upward. So then it's decreasing when it looks like it's moving downward. So from here right up to 1, right? And I'm looking at the x-axis, by the way, when I'm listing these values. So from there right up to 1. And then it looks like it also decreases from here to here, right? That tiny little interval. So that would be from, well, since there's an arrow, that go from negative infinity up to 1. And then it picks up at 3 to 4. So I'll use the union symbol. And note that we always use open intervals, the parentheses in interval notation for these. We don't actually ever include the actual value of the endpoint. We just use parentheses every time we put this information. Okay, so another concept that we're interested in is this idea called local extrema. So a point where a function changes from increasing to decreasing is called a local maximum. So let's go back up here to this picture we had, a local maximum. Oops. So that's going to happen when it goes from increasing to decreasing. So like right here would be a point where the graph goes from climbing upward, right, to climbing downward, increasing to decreasing. So that point right there would be called a local maximum. Oops. Okay. Then a minimum would be when it goes from decreasing to increasing, the opposite, local minimum. And they call that any local minimum or local maximum, which the plural is local maxima, local minima. Those are called local extrema, or they also are sometimes referred to as extreme values for the function. So that's something you could possibly see using a different textbook. That might be the phrasing they use. Okay, so here, let's go back to an example we saw earlier with the gasoline. Understanding the idea of increasing and decreasing now, we're interested to see if we have any local extrema, any points that would be like a maximum or a minimum. And the truth is we kind of talked about it when we were looking at the original example, this example previously. So the idea is we could kind of see that it's increasing, right? It keeps climbing in value all the way to there. So from here to there, all of these values are increasing. Mark that, increasing. But then right here, for the first time, it decreases. So that means that this point could potentially be what we could call a local max, because it goes from increasing to decreasing. So we would have a local maximum, and I'll just put local max, at t equals 8. Or another way of saying that is oh, I also realized that it asks us to list where the interval appears to be decreasing. Okay, we'll do that in just a second. Looks like we have a local max at t equals 8, or I could say c of 8 equaling 3.01 is potentially a local maximum. And then this thing is decreasing from, let's see, find an interval in which the function appears to be decreasing. So I guess I would say from 9 and 8 to 9. So from 8 to 9 would be where it'd be decreasing in value. And I think that's what they're after. I think that's all they're really after. Okay, so let's use a graph to estimate the local extrema, but this time they didn't actually give us the graph. So we're going to need to graph this. Now, this is a point in the class where I would encourage you to use some graphing software. I tend to use Desmos. So if you go to desmos.com, you will see this. And this is a free graphing calculator. There is another really common one called GeoGebra, and there are some others out there, but this is the one I'm going to use in this class. So let's go ahead and I'll show you how to use this. Let me go and get rid of these downloads here. All right, so graphing calculator, just click that. You don't have to sign in or anything like that to use it. And we're going to enter that function. Now, here's what's cool. You can enter f of x. It has no problem with you saying f of x, but you could also put y equals, doesn't really matter, 2 over x. So for the over button, I'm using slash 2 over x. I'm going to arrow, make sure I put plus x over 3. And there we go. There's a graph. Now, from here, we are going to attempt to find maximums and minimums. And it does look like maybe we have a low point somewhere over here, right? Some sort of low value, and then maybe a high point over here. So this would potentially be a local max, and this would potentially be a local minimum. So what I'm interested in is seeing if this point does in fact represent, that maximum or minimum at these values, those little points that they kind of labeled on here. So one way I can do that is to select a table to kind of look at the values and see. So if I come over here and I hit this little cog right above the equation, this gives me the option to have a table of values. And as you can see, it'll give me values that they've already kind of pre-figured out for me on the function. And they even highlighted them in red for me. Wasn't that nice? Okay. Now 2.49 was the one that it looked like it was potentially a low point. So that's definitely not as low, or yeah, lower than the value at 2. I'm going to check 2.5 just to see. So it was 499. So I'm looking like it might be 2.5 is the low point right there. That's this point right there. Oh, again, they highlighted it as 2.449. So 2.449 seems to be that kind of magic number. They're rounding on the table, but they did pre-highlight it for us. So that was nice. If I go ahead and get rid of this and try to locate those values again, negative 2.499 and positive 2.499. So those would be the local maximum and minimum values. All right, so let me go ahead and go back to my notes to write that down. So this is what I'd expect to see, or what you'll do on the homework is then you'll indicate what those values are. So we had a local minimum at 2.449. And it was, sorry, here, let me switch back over to see what the value was, 1.633. And then a local max at the negative of this, 2.4. Oh, I'm sorry, I should have been 99. 99 and negative 1.633. And that's how you'd answer that question. You would just use a graphing program, and that's it.